Hi class, this is the video for lesson 75, our last lesson of the week. Hopefully you've watched all of them. I want to do a couple of review problems, then I'll get into the lesson for today. It's on implied ratios, more on ratios. And these are going to relate to story problems. So how to pick a ratio out of a story problem and solve for the information you're looking for. In our review, we're going to work a story problem with ratios also. These related to speed. I thought it would be a good time to review this. This was a little bit more complex because it dealt with those two equations. If you remember, it introduced these two equations: distance equals rate times time, and time equals rate times distance. And the rates referred to were different. So if you were solving for distance, you would use one rate. If you're solving for time, you would use a different one. So I'm going to review a problem with speed and how we decide which of these equations we use and which rate we use. This was an actual problem. It's number 2 in lesson 75, and it's not assigned, so I'm going to work it with you here. Let's read the problem. Etzel traveled the 350 miles to the Rouge plant in 7 hours. The next day, he was in a hurry to return. How fast would he need to drive to complete the return trip in 5 hours? Sometimes story problems will give you information. It can be a little tricky that you don't actually need. So you have to be careful that you hone in and you pick out what information do I actually need to convert this to a math problem and what don't I need. Don't get confused. If you read carefully, it's asking how fast does he need to drive on his return trip. We don't really need to know how fast he drove there because all we're trying to find out is how fast does he need to come back on the return trip to make it in 5 hours. We do need to know how far he's driving. We don't really need to know this information here. But I'm going to use this information to remind you how to calculate speed, which, if you recall, is a ratio with time on the bottom. So our problem tells us that he drove 350 miles in 7 hours. We always want a single unit of time on the bottom when we calculate speed. So we'll go ahead and divide 7 into 350, and that's 50. And that tells us that Etzel was driving 50 miles per hour. This is a rate of speed there with time on the bottom. Now, we want to find out the rate of speed on his return trip. So we want our answer is going to be a rate of speed. It was, if you recall, this is the problem in which we use rate of speed when we're trying to solve for distance. So we're looking for a rate right here. This is the one that involves rate of speed. So I'm going to choose this equation here to find my answer. Distance equals rate times time. Let's see. So we're given the distance. It's 350 miles equals, we need the rate, and we're given the time. He's got to return in 5 hours. All right. So rate is a ratio. I'm sorry, speed is a ratio. It's a ratio. And so our answer is going to be in miles per hour. But if you think about it, if you look at my speed right here, we calculate our speed in distance over a single unit of time. And 50 over 1 is really just 50. So for the purpose of solving this problem, I don't have to worry about a fraction here. Let's just look for our single value, and that's going to end up being our numerator of our speed. In other words, just looking for a single value for rate is going to make our problem easier. Now what I have is, I'm going to drop my units for a moment and make this simple. 350 equals 5r. Let's solve for r. We need to divide both sides by 5. 5 goes into 350. 70 times. These 5s cancel, and that leaves me with r. So our rate is 70, but of course we want this as a rate of speed. How do we rate speed? It's going to be 70 miles per 1 hour, and that's our rate. That's his speed. So on his return trip, to make it back in 5 hours, Etzel needs to drive 70 miles per hour. So don't get too confused on these speed problems. Remember, the distance equals rate times time, and the time equals rate times distance. When you solve for a rate, Just find a single value and then put it in the proper units like I did here. Okay? So I'm going to erase that. There we go. Alrighty. And the other one is quicker, but I want you to pay attention. It's good to do some review. I don't see you in class, so I can't do the review there. So stick with me here while I do one more. This is actually lesson 4 in lesson 75. 4/5 of the bees were not in the hive. Not in hive. I'm going to abbreviate a little bit. And by the way, you know you'd never start a sentence with a numeric value. That would have to be written out. But I'm trying to hurry and not take too much of your time. 4/5 of the bees were not in the hive. If 1,350 bees were in the hive, how many were out of the hive? How many? Oh, wow, out. Pretty sloppy. Okay, so we're given the ratio 4/5. We can deduce the other ratio from that. If 4/5 are not in the hive, how many are in the hive? Obviously, 1/5 are in the hive. 350 are in the hive. So we see that 350 are in the hive. This is the actual amount in the hive. Okay, let's use the ratio 1/5. This is the fraction that represents how many are in the hive. 1 out of 5 are in the hive. Let's set that up as a proportion. We know that this is the number that are in out of the total. 1 out of every 5. Let's look at the actual number. 1,350 are in out of some total number. Once we find the total number of bees, I just subtract how many are in the hive and I know how many are out of the hive. So let's do our cross multiplication. 1 times t is t. 1,350 times 5, I worked that out, that's 6,250. So this tells us that there's a total number of bees that are 6,250 total bees. The total minus the number that are in the hive gives us the number that are out of the hive. 12 minus 3 is 9, 5 minus 1 is 4. 4,900 bees are out of the hive. Okay, so just when you read these problems, just pick out carefully what your ratios are going to be, set up your conditional proportion with your value that you're looking for, and then make sure that you have whatever you're representing on the top in the numerator, you're also representing over here. If this is the number that represents how many are in the hive, then this has to be my actual number in. If this represents the total the total number of bees, this t here will represent the total on the bottom. So our denominators have to match and our numerators have to match. All right, let's move on to this week's lesson. All right, this week they're talking about implied ratios. All that means is that they're giving you story problems where you have to pick out ratios and set up a proportion yourself. Typically, so far, they've said things like the ratio of, nice boys to not nice boys was 3 to 5. They'll actually use the word ratio in your problem. Now they're not going to do that anymore, and you have to be a detective and figure out how to set up your ratio on your own. And so it's just another step in analytical thinking. This is really good for you. These story problems, try to look at them as a brain teaser or a challenge. It's so good to learn how to think analytically. So this is my example here. It takes 5 pre-algebra students to lift a 145-pound box of math books. How many students will it take to lift a 725-pound box of math books? All right. Let's kind of hone in on our information. 5 pre-algebra students, 145-pound box, 725-pound box. There's our numeric values. Do we need them all? Well, remember we're setting up a conditional proportion. It should have 3 out of 4 values. And then we're looking for the last value, which is going to tell us how many pre-algebra students to lift that heavier box. So what is our implied ratio? It takes 5 pre-algebra students to lift a 145-pound box of math books. So 5 for 145 pound. 5 students, 145 pounds. That's our ratio. How do we set up our proportion? All right, we have we have some more information in pounds. Remember how I told you the denominators have to match type of information? If we're referring to the box on the bottom in this ratio, I want the new denominator to also, in my second ratio is going to be, sorry, I'm talking over myself. We're going to represent pounds in the denominators in both ratios. Right? We're going to set them equal to each other, and then this is the information we're looking for. If this refers to how many students, then the numerator in the other ratio needs to refer to how many students. All right, so we have 5 is to 145 as some number of students is to 725. All we have to do now is cross multiply. I didn't work this out, darn, sorry. I'll do it quickly. 12, 1, 35, 36. Okay, so 5 times 725. I like to put my variables on the left, so we'll say 145 times x equals 725 times 5, which is 3,625. I'm going to divide both sides by 145. I want x all by itself on the left. Those are going to cancel. I'm going to torture you with some long division here. Looks like that's going to go in 2 times. That's 290. Subtract 290 from 362. 16 minus 9 is 7. All right, and then we'll drop down our 5. 145 goes into 725. I do believe that is 5. 290 and 290 is 580. Okay, that's 5. You know, long division's a little trial and error. Yeah, that's right. All right, so, and then that comes out evenly to 725 with no remainder. So if it takes 5 students to lift a 145-pound box, it will take 25 students, all right, to lift 725-pound box. All right, and that's how we work these implied ratios. We're picking out our condition, we're setting up our conditional proportion with a little less information. They're not just handing you the rate. You have to look at the problem and figure it out on your own. So, all right, I think you can do it. Signing off.